Alright, so in this video I'm going to be explaining another approach for domain adaptation. This time is in the setting of unsupervised learning, and the measure that we need for this domain adaptation is maximum. We should maximize the classifier discrepancy. So this is paper in 2018. In this work, we present a method for unsupervised domain adaptation. Many adversarial learning methods train domain classifier networks to distinguish the features as either a source or target, and train a feature generator network to mimic the discriminator. Two problems exist with these methods. First, the domain classifier only tries to distinguish the features as a source or target, and thus does not consider task-specific decision boundaries between classes, because it only tries to match these two, align them together. It doesn't care about if they are from, for example, a different class. Different classes should be separated in this mapping. Therefore, a train generator can generate ambiguous features near class boundaries. Second, these methods aim to completely match the feature distributions between different domains, which is difficult because of each domain's characteristics. To solve these problems, we introduce a new approach that attempts to align distributions of source and target by utilizing the task-specific decision boundaries. We propose to maximize the discrepancy between two classifiers' outputs to detect target samples that are far from the support of the source. A feature generator learns to generate the target features near the support to minimize the discrepancy. Our method outperforms other methods on the several datasets of image classification and semantic segmentation. So previous methods just try to deceive the domain classifier and neglect the classes. But the proposed method, as you see, stars are together, and circles are together. And we also minimize the discrepancy. So left is previous methods try to match different distributions by mimicking domain classifier. They do not consider the decision boundary. Because after adaptation, you see this decision boundary is wrong, because you have plus on both sides. But on the right, as you see, all pluses go together. So there are three contributions in this nice paper. We propose a novel adversarial training method for domain adaptation that tries to align the distribution of a target domain by considering task-specific decision boundaries. We confirm the behavior of our method through a toy problem. We extensively evaluate our method on various tasks: digit classification, object classification, and semantic segmentation. So this is an example of two classifiers with an overview of the proposed method. Discrepancy refers to the disagreement between prediction of two classifiers. First, we can see that the target samples outside the support of the source can be measured by two different classifiers. Second, regarding the training procedure, we solve a minimax problem in which we find two classifiers that maximize the discrepancy on the target sample and then generate features that minimize this discrepancy. We have access to a labeled source image and a corresponding label drawn from a set of labeled source images, as well as an unlabeled target image drawn from unlabeled target images. We train a feature generator network which takes inputs x sub s or x sub t and classifier network f sub 1 and f sub 2. These are classifier which take features from the G. f1 and f sub 2 classify them into k classes. That is, they output a k-dimensional vector of logits. We obtain class probabilities by applying the softmax function for the vector. We use the notation p sub 1 and p sub 2 of probability of y condition on x to denote k-dimensional probabilistic output for input x obtained by f1 and f2 respectively. The goal of our method is to align source and target features by utilizing the task-specific classifiers as a discriminator in order to consider the relationship between class boundaries and target samples. For this objective, we have to detect target samples far from the support of the source. The question is how to detect target samples far from the support. These target samples are likely to be misclassified by the classifier learned from source samples because they are near the class boundaries. Then, in order to detect these target samples, we propose to utilize the disagreement of the two classifiers and the prediction for target samples. So consider two classifiers f1 and f2 that have different characteristics. We assume that these two classifiers can classify source samples correctly. And this assumption is realistic because we have access to labeled source samples in the setting of unsupervised domain adaptation. In addition, please note that f1 and f2 are initialized differently to obtain different classifiers from the beginning of train. We have the key intuition that target samples outside the support of the source are likely to be classified differently by the two distinct classifiers. This region is denoted by black lines, so we call it discrepancy region. Conversely, if we can measure the disagreement between the two classifiers and train the generator to minimize the disagreement, the generator will avoid generating target features outside the support of the source. So there are different steps. First, we fix our generator and then we learn our classifiers. Then we update G, but we fix the classifiers. And I will go through all of them. But we utilize the absolute value of difference between two classifiers. You see, we have two classifiers, F1 and F2. Each one has a different probability condition of Y, condition of X. So we need a discrepancy between them. Because your target sample can come here and different classifier can classify it differently. So we utilize the absolute value of difference between the two classifiers, probabilistic outputs, as discrepancy loss, where P1 and P2 is the probability of P1, P2 for class K, respectively. And the choice of L1 distance is based on the theorem, and we we experimentally found that L2 distance does not work well. So training steps, we have 3 steps, A, B, C. For step A, we train both classifiers and generator to classify the source samples correctly. So we just use it for source samples. In order to make classifiers and generator obtain task-specific discriminative features, this step is crucial. We have 2 kinds of features, by the way. We have, I call it domain invariant features and domain specific features. And so if this is my feature space, I say that, for example, the upper side is domain invariant, and the lower side depends on the domain, has a different feature. So step A, as I said, we train both classifiers for the source. So as you see, F1 and F2 are, we want to know which one is better. F1 has parameters, F2 has parameters, G has parameters, G is generator. And so we have this loss, which is expectation of this log of probability of Y given XS. But in step B, we train classifiers as discriminator for a fixed generator. By training the classifiers to increase the discrepancy, they can detect the target samples excluded by the support of the source. This step corresponds to step B in the figure that I showed you. And we add a classification loss on the source samples. Without this loss, we experimentally found that our algorithm performance drops significantly. We use the same number of source and target samples to update the model. So we have some adversarial, so this is the discrepancy between P1 and P2, the discrepancy loss. And in step C, which is the final step, we train the generator to minimize the discrepancy for fixed classifier. This step corresponds to step C. The number n indicates the number of times we will repeat this for same mini-batch. This number is a hyperparameter. This term denotes a trade-off between generator and classifiers. Because the tuning the frequency, some of them learn very fast. Some of them have a different speed for learning. So we should tune them very adequately. So step C, we see that we are minimizing the discrepancy on the target because we have fixed our classifiers and we just update our generator. Very elegant idea. But what is the theoretical insight behind it? Given 2 domains S and T, S is here, T and here, this is the error of the hypothesis H on the target domain and on the source domain. This I is the indicator function, which is 1 if predicate is true and 0 otherwise. So it is upper bounded by the source plus this d of h, which is here. So for experiments, if your source is this street view, and then we go to MNIST data, you have 67% if it is only source. But in our approach, we have 96%, which shows that this method works very well.